There's something about the night sky that has always tugged at our curiosity. Those pinpricks of light aren't just stars. They're silent storytellers, whispering secrets that have rewritten human history. For millennia, we've gazed up, searching for answers, and along the way, we've stumbled upon revelations so profound, they shattered everything we thought we knew. Picture this, 30 cosmic landmarks, each a turning point that cracked open the universe's grand narrative. From the first time a telescope revealed Jupiter's moons to the moment we captured the shadow of a black hole, these discoveries didn't just change science, they redefined reality itself. Whether you're someone who can name every constellation or just occasionally glance up in wonder, this journey will leave you seeing the cosmos differently. Because these aren't just facts, they're the moments that stretched our minds to the edges of existence, ready to explore the celestial breakthroughs that made us rethink it all. Let's begin. Think about how unsettling it must have been when humanity first realized we weren't the center of the universe. Before Copernicus, the idea that Earth stood motionless while everything else revolved around us seemed unquestionable. After all, it matched what our eyes saw every day. But when he published his groundbreaking work in 1543, arguing that the sun anchored our cosmic neighborhood instead, it sparked more than just scientific debate. It shook the foundations of philosophy, religion, and even our sense of identity. Imagine living in a world where every institution told you the heavens moved for you, only to learn you were just another speck orbiting a star. Galileo's telescope turned this theory into undeniable truth when he spotted Jupiter's moons circling another world, proving Earth wasn't uniquely privileged. This wasn't just about swapping one cosmic model for another. It was the moment humanity began to grasp its true scale in the vastness of space. And as we'll see next, that humility paved the way for another revelation hiding in the subtle dance of the planets. Copernicus and Galileo may have knocked Earth from its pedestal, but it was Johannes Kepler who unveiled the hidden choreography of the heavens. Picture the frustration of early astronomers, struggling to force the planets' paths into perfect circles only for Kepler to prove they moved in elegant ellipses, with the sun not at the center but as a focal point, like a cosmic conductor guiding the orchestra. His first law shattered 2,000 years of celestial perfectionism, but the real magic lay in what came next. Planets don't wander aimlessly, they speed up in a fiery sprint near the sun, then slow to a leisurely stroll in the colder depths of space, sweeping equal areas in equal times, a rhythmic cadence captured in his second law. And then came the masterstroke, his third law, a precise mathematical harmony linking a planet's orbital period to its distance from the sun, as if the universe had left us a sheet music of gravitational relationships. Suddenly, the cosmos wasn't just orderly, it was calculable. Kepler's laws became the Rosetta Stone for Newton's gravity, proving that the heavens spoke the language of mathematics. And with that revelation, humanity took its next step toward unlocking the force that binds the universe together. That falling apple in Newton's garden did more than inspire a eureka moment. It revealed a cosmic rulebook written in the language of gravity. Until then, the force that kept planets in orbit seemed like a celestial mystery, entirely separate from the mundane world of falling objects. But Newton's genius lay in seeing the connection. The same invisible pull that sent an apple plunging earthward also kept the moon tethered to our planet and Earth itself circling the sun. His law of universal gravitation wasn't just an equation. It was a radical equalizer, declaring that every speck of matter in the universe, from a grain of sand to a swirling galaxy, played by the same rules. Suddenly, the tides weren't just ocean currents but the moon's gravitational whisper, and Halley's comet wasn't a divine omen but a predictable traveler obeying mathematical destiny. What made this breakthrough earth-shaking wasn't just its accuracy, it was its universality. For the first time, humanity held a key that could unlock motion anywhere, from a child's tossed ball to the dance of binary stars. And yet, as comprehensive as Newton's framework seemed, it left one gaping question unanswered. What carried this invisible force across the emptiness of space? That puzzle would linger for centuries until a patent clerk named Einstein reimagined gravity itself, but that's a landmark for later. For now, Newton's insight gave us something equally powerful, the audacious idea that the cosmos could be understood, calculated, even mastered. And with that confidence, we turned our attention to a new cosmic messenger light. While Newton revealed how gravity moved the heavens, it took a humble prism to prove we're made of the very same stardust we admire. Enter spectroscopy, the art of reading light like a cosmic fingerprint. In the mid-1800s, Gustav Kirchhoff and Robert Bunsen noticed something peculiar. When elements like sodium or iron were heated, they didn't just glow randomly. Each emitted a precise pattern of colored lines as distinctive as a barcode. But the real magic happened when they pointed their prism toward sunlight. Those same telltale lines appeared, revealing a startling truth: the sun wasn't some mystical fire, but a blazing ball of familiar elements, the same ones found right here on Earth. Suddenly, the universe felt less alien. Spectroscopy became astronomy's decoder ring, allowing us to eavesdrop on the chemical whispers of stars millions of light years away. Consider helium, discovered in the sun's spectral lines decades before it was ever isolated in a lab, proof that the cosmos hides secrets even in plain sight. Beyond mere ingredients, these light patterns unveiled celestial dramas: the violent swirl of newborn stars, the death throes of supernova, even the ghostly glow of interstellar gas. Every hue and shadow in a spectrum tells a story, and thanks to this 19th century breakthrough, we learned to listen. Now armed with the ability to dissect starlight, astronomers faced an even grander challenge, measuring not just what the universe is made of, but how impossibly vast it truly is. Measuring the universe required more than just keen eyes. It demanded a ladder of cosmic clues, each rung allowing us to reach further into the abyss. For centuries, even our sharpest minds could only guess at the true distances to the stars, trapped in a celestial hall of mirrors where bright objects might be dim and far, or faint ones could be deceptively close. Then came Henrietta Swan Leavitt, a meticulous observer of variable stars, who noticed something extraordinary about Cepheids. Their rhythmic pulses held a secret. The longer a Cepheid took to brighten and dim, the more luminous it inherently was, like cosmic lighthouses whose flicker patterns betrayed their true wattage. Suddenly, astronomers had their first reliable yardstick: find a Cepheid in the void, clock its pulse, and calculate its distance with stunning precision. This humble breakthrough became the foundation of the cosmic distance ladder, the step-by-step method we still use today to map the universe's vastness. But the real shock came when Edwin Hubble trained his telescope on the fuzzy patch known as the Andromeda Nebula. Nestled among its swirling dust, he spotted Cepheids blinking their coded message, and their staggering distance revealed the unthinkable. Andromeda wasn't a nebula at all, but an entire galaxy, a twin of the Milky Way drifting millions of light years away. In one stroke, the universe exploded in size, transformed from a solitary starry disk into a sprawling metropolis of galaxies, each an island of billions of suns. The implications rippled far beyond astronomy. Philosophers grappled with a cosmos suddenly devoid of center or edge, while artists and poets wrestled with the vertigo of infinite space. Even science itself had to adapt, as distances once deemed unimaginable became routine entries in celestial ledgers. Today, the cosmic distance ladder stretches from radar pings off nearby planets to the redshift of galaxies fleeing at the edge of the observable universe, each step calibrated by Cepheids, supernova, and other mile markers Leavitt could never have dreamed of. And yet, for all its precision, this ladder revealed something even more startling. The universe wasn't just vast, but growing, stretching itself apart like rising bread. And that discovery would lead us to our next cosmic landmark, the echoes of creation itself. Hubble's telescope didn't just reveal galaxies beyond our own, it caught the universe red-handed, fleeing in all directions like a cosmic crime scene in reverse. When Edwin Hubble meticulously measured the redshifts of distant galaxies in the 1920s, he uncovered something bizarre. The farther away a galaxy was, the faster it seemed to be racing away from us. This wasn't just random motion, it was a pattern so precise it became Hubble's law, a mathematical testament to an expanding universe. Imagine baking raisin bread where the dough rises, carrying the raisins apart, except here, the dough is space itself, stretching galaxies away from each other without them actually moving through it. This single observation shattered centuries of belief in a static, unchanging cosmos. If everything was rushing apart now, logic suggested that rewinding time would compress the universe into an unimaginably hot, dense speck, a starting point we now call the Big Bang. The implications were staggering. Philosophers and theologians had debated creation for millennia, but suddenly, science had something to say. The universe had a birthday. Yet Hubble's discovery left a haunting question: what if this expansion never stopped? Would galaxies vanish over the horizon of space, leaving future astronomers with an empty sky? Or would gravity pull everything back in a cosmic reversal, a big crunch to bookend the beginning? Hubble's work didn't just change astronomy, it forced humanity to confront the universe's mortality. But the most breathtaking evidence for this explosive birth wasn't found in distant galaxies. It was lurking in the static of a television antenna, waiting to be stumbled upon by two very surprised radio engineers. That faint hiss of static plaguing Arno Penzier's and Robert Wilson's radio telescope wasn't just faulty equipment, it was the universe itself murmuring its origin story. What they dismissed as pigeon interference in 1965 turned out to be the oldest light in existence, a ghostly whisper from a time when the cosmos was a searing plasma just 380,000 years old. This cosmic microwave background, cooled over 13.8 billion years to a faint 3 degrees above absolute zero, became the ultimate confirmation of the Big Bang. Imagine holding a photograph of the universe as a newborn, its faint temperature variations, those tiny bumps in the data revealing the seeds of everything, the future homes of galaxies, stars, and planets. But the CMB's revelations didn't stop there. When satellites like COBE and Planck mapped its subtle imperfections with exquisite precision, they uncovered something even more profound. Those minuscule fluctuations were the universe's first handwriting, scribbled by quantum ripples stretched across space during inflation, a violent exponential growth spurt in the first fractions of a second. Without those primordial wrinkles, gravity would have had nothing to amplify, no cosmic scaffolding to pull matter into the vast web of galaxies we see today. What's staggering isn't just the CMB's role as a time capsule, it's how this ancient light continues to surprise us. Its polarization patterns hint at gravitational waves from the universe's first moments, while its uniformity, nearly identical in all directions, poses existential riddles about what lies beyond our observable horizon. Even now, this afterglow serves as a forensic snapshot, helping physicists weigh invisible dark matter, measure the universe's shape, and test wild theories like parallel bubble universes. Yet for all its clarity, the CMB also exposed our biggest blind spot. Those meticulous maps revealed that ordinary matter, the stuff of stars, planets, and us, makes up less than 5% of the cosmos. The rest, a mysterious cocktail of dark matter and dark energy, forces so elusive they defy detection but shape the universe's fate. And it was another cosmic landmark, hidden in the sway of spinning galaxies, that first betrayed dark matter's invisible grip. Vera Rubin didn't set out to upend cosmology, she just wanted to measure how galaxies spin. But when her meticulous observations of the Andromeda Galaxy in the 1970s revealed stars at the edge whipping around just as fast as those near the core, it wasn't just unexpected, it broke the rules. According to Newton's laws, those outer stars should have been sluggish, like children at the end of a merry-go-round struggling to hold on. The fact that they weren't meant only one thing. Something invisible, something massive, was holding galaxies together with gravitational hands we couldn't see. This phantom force, later dubbed dark matter, wasn't some faint trace element. It outweighed ordinary matter 5 to 1, a shadowy scaffold stretching across the cosmos. Picture a snowy field at night. The visible flakes might dazzle, but the real weight comes from the trillions more you can't see beneath the surface. Rubin's discovery forced astronomers to confront an unsettling truth. We'd been studying the universe with blinders on, mistaking the glitter for the bulk. Yet dark matter's strangeness doesn't stop at its invisibility. Unlike atoms, it refuses to interact with light or collide with itself, passing through galaxies like ghosts through walls. We only know it's there because of its gravitational pull, bending spacetime like a hidden hand pressing down on a mattress. Modern telescopes map its presence indirectly, tracing the way it distorts distant starlight or sculpts the web-like structure of the cosmos. Without it, galaxies would fly apart, and the universe as we know it wouldn't exist. Rubin's work didn't just add a new ingredient to the cosmic recipe, it rewrote the entire menu. Suddenly, everything from the universe's expansion rate to the fate of galaxy clusters hinged on this enigmatic substance we still can't directly detect. Decades later, dark matter remains one of science's most tantalizing puzzles, with experiments hunting for hypothetical particles like WIMP or actions in mile-deep mines and particle colliders. But even as the search continues, Rubin's legacy stands as a humbling reminder. Sometimes the universe's greatest revelations come not from what we observe, but from the glaring inconsistencies we can't ignore. And just when we thought the cosmos couldn't get any stranger, another invisible force was waiting in the wings, one that wouldn't pull galaxies together, but push them apart with terrifying speed. Dark energy wasn't just hidden. It was hiding in plain sight, masquerading as an observational error until it upended everything. When two independent teams of astronomers trained their telescopes on distant supernova in 1998, they expected to measure how much the universe's expansion was slowing down, pulled back by gravity's relentless tug. Instead, they found the opposite. These cosmic explosions, acting as mile markers across deep space, were dimmer than they should have been, meaning space itself was stretching faster than anyone predicted. The universe wasn't just expanding, it was accelerating, as if some invisible foot had slammed on the cosmic gas pedal. The culprit, a placeholder name for our ignorance, dark energy. Unlike dark matter's gravitational embrace, this force does the opposite. It pushes, driving galaxies apart with a strength that grows as the universe expands. The numbers defy intuition. Dark energy makes up roughly 68% of the universe's total energy content, dwarfing both dark matter and ordinary atoms combined. Imagine blowing up a balloon covered in dots. Dark energy isn't just making the balloon inflate, it's ensuring each dot races away from its neighbors faster with every passing second. What makes this discovery so unsettling isn't just its sheer dominance, but how stubbornly it resists explanation. The leading candidate, Einstein's old cosmological constant, a sort of anti-gravity he once called his greatest blunder, now resurrected as the energy of empty space itself. But here's the catch. Quantum theory predicts vacuum energy should be astronomically stronger than what we observe, leaving physicists grappling with a discrepancy of 120 orders of magnitude. Other theories propose evolving fields or extra dimensions, but every idea comes with its own paradoxes. The implications ripple far beyond equations. If dark energy's push continues unchecked, distant galaxies will eventually vanish beyond our cosmic horizon, their light stretched into oblivion. A trillion years from now, astronomers in our Milky Way might peer into a starless void with no evidence other galaxies ever existed. Yet for all its mystery, dark energy wasn't the last cosmic surprise, just the prelude to an even stranger discovery, one that wouldn't whisper through light or gravity, but send tremors through the fabric of space-time itself. Einstein didn't just predict gravitational waves, he doubted we'd ever detect them. These faint ripples in space-time, born from cosmic catastrophes like black holes colliding, stretch and compress the fabric of reality itself by distances smaller than an atom. For decades, scientists chased this phantom signal, building instruments so precise they could measure a change in length equivalent to a human hair's width across the distance to the nearest star. Then, on September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught something extraordinary, a fleeting chirp lasting less than a fifth of a second. That whisper, emitted by two black holes merging over 1.3 billion years ago, marked the first direct detection of gravitational waves, a triumph a century in the making. What made this discovery revolutionary wasn't just the confirmation of Einstein's theory. It was the birth of an entirely new way to explore the universe. Traditional astronomy relies on light, but gravitational waves slip through cosmic dust, black hole horizons, and even the dawn of time itself, carrying secrets ordinary telescopes can't touch. When LIGO later detected neutron stars colliding in 2017, the event didn't just send gravitational tremors, it also unleashed a firework of gamma rays, light, and heavy elements like gold and platinum, proving these violent mergers forged the universe's precious metals. Suddenly, we weren't just observers of the cosmos, we were eavesdroppers on its most hidden symphonies. The implications stretch far beyond Einstein's equations. Gravitational waves let us test general relativity in extreme environments, probing whether black holes truly have no hair, a poetic way of saying they're defined only by mass and spin. They've revealed unexpected populations of hefty black holes, puzzling astronomers with their sheer size. Future observatories like the space-based LISA aim to catch waves from supermassive black holes merging in the early universe, potentially uncovering clues about inflation or even extra dimensions. But perhaps the most profound realization is this: space-time isn't just a static stage where cosmic events unfold. It's a dynamic, vibrating membrane, ringing like a bell with every cataclysmic collision. And now, thanks to LIGO, we've tuned our instruments to listen. For centuries, black holes existed only as mathematical curiosities, dark prisons from which not even light could escape, their very existence debated because how do you photograph the absence of light? Then, in April 2019, humanity stared into the abyss and the abyss stared back. The Event Horizon Telescope's image of the supermassive black hole at the heart of galaxy Messier 87 wasn't just a scientific triumph, it was a visceral encounter with cosmic scale. That haunting orange ring, photons twisted into a fiery halo by spacetime's extreme curvature, framed a darkness so absolute it punched a hole in the universe's fabric. What made this image revolutionary wasn't just its visual impact, but the staggering engineering behind it. 8 radio telescopes spanning from Hawaii to Antarctica synchronized their observations with atomic clock precision, effectively creating a virtual telescope as wide as Earth itself. The data collected 5,000 trillion bytes was so vast it had to be physically flown on hard drives to supercomputers for analysis. For 2 years, researchers meticulously pieced together this cosmic jigsaw, revealing a structure that matched Einstein's equations down to the last decimal. That shadow at the image heart, the event horizon silhouette, its size betraying the black hole's monstrous mass 6.5 billion times our sun's, crammed into a space smaller than our solar system. Beyond confirming what we'd theorized for decades, this image cracked open new ways to study these gravitational titans. The asymmetry in the glowing ring hinted at the black hole's spin, while its shape tested general relativity under conditions no lab could ever replicate. Suddenly, we had a new tool to probe questions that once seemed untouchable. How do black holes launch jets of matter at near light speed? What happens to information swallowed by their singularity? Even the black hole's shadow, slightly smaller than predicted, sparked debates about alternative gravity theories. But perhaps the most profound revelation was how this achievement redefined observational astronomy's limits. If we could image a black hole 55 million light-years away, what else might we capture? The same global array now trains its sights on Sagittarius, a star, the supermassive black hole at our Milky Way's core, while plans for space-based telescopes promise even sharper views. This milestone didn't just make the invisible visible, it proved that with enough ingenuity, even the universe's most elusive secrets leave fingerprints we can trace. And as we turned our attention from these cosmic vacuum cleaners, another discovery was reshaping our place in the cosmos, not in the voids between stars but around them. For centuries, the idea of planets circling distant stars lived only in science fiction until one groundbreaking night in October 1995, when Swiss astronomers Michel Mayor and Didier Queloz pointed their telescope at 51 Pegasi and caught a wobble. That subtle back and forth dance of the star revealed something revolutionary. A giant planet, half Jupiter's mass but orbiting so close to its sun that a single year lasted just 4 Earth days. 51 Pegasi b wasn't just an oddity, it defied every textbook model of planetary formation, proving the cosmos loves surprises. Suddenly, our solar system's orderly architecture, rocky inner planets, gas giants patrolling the outskirts, wasn't the universal blueprint we'd imagined. Astronomers began finding hot Jupiters hugging their stars, planets with diamond rain, even worlds orbiting the corpses of dead stars. But the real game-changer came with NASA's Kepler space telescope, a planet hunting machine that stared at one patch of sky for 4 years, monitoring 200,000 stars for the telltale dimming of a passing world. Its treasure trove of data revealed something staggering. Planets outnumber stars in our galaxy, with billions likely Earth-sized and orbiting in their star's habitable zone, that Goldilocks distance where liquid water could pool. Consider Kepler 452b, the first near-Earth-sized planet found in a habitable zone, or the TRAPPIST-1 system's 7 rocky worlds, 3 of which might harbor oceans under their skies. These discoveries didn't just expand our cosmic address book, they rewrote the rules of planetary science. We now know gas giants can migrate inward, that binary stars host planets too, and that multi-planet systems often outnumber lone worlds. Even our definition of habitable has stretched. Could life thrive in the subsurface oceans of frozen exomoons, or on tidally locked planets with eternal daysides? The hunt for exoplanets has become a technological arms race, with instruments like JWST sniffing atmospheres for biosignatures, oxygen, methane, even industrial pollutants. Private initiatives like Breakthrough Starshot dream of sending nanoprobes to nearby systems, while next-gen telescopes aim to directly image Earth twins. But perhaps Mayor and Queloz's greatest legacy is this. By proving other suns host planets, they transformed the search for alien life from philosophical speculation to a testable hypothesis. And as we turned our gaze outward, another frontier was beckoning closer to home, one where rovers scoured rusty deserts for clues to life's cosmic ubiquity. Mars wasn't always the rusty desert we see today. It used to wear water like a second skin. When NASA Mariner 9 became the first spacecraft to orbit another planet in 1971, it sent back images that stunned scientists. Dry riverbeds snaking across the surface, canyons carved by ancient floods, and sediment layers that looked like pages from a geological history book. But it took decades of robotic explorers to turn those hints into undeniable proof. Viking landers scooped rust-colored soil in the 1970s. Pathfinder bounced to the surface in '97 with its tiny Sojourner rover, and Spirit and Opportunity spent years driving through what were once lake beds and hot springs. Each mission peeled back another layer of Mars' watery past, revealing a planet that once had lakes as deep as the Mediterranean and rivers as wide as the Mississippi. Then came Curiosity in 2012, rolling into Gale crater like a robotic geologist on a mission. Its drill pulled up mudstone laced with clay minerals rock that could only form in standing water. But the real jaw-dropper came when it found organic molecules, the carbon-based building blocks of life, preserved in 3-billion-year-old mud. Suddenly, the question wasn't just whether Mars had water, but whether it once cradled life in those vanished shorelines. Perseverance, landing in 2021, took the hunt even further, caching samples from an ancient river delta where microbial life might have thrived, samples that could one day be returned to Earth for analysis. The intrigue doesn't stop at fossils. Mars still whispers with watery secrets today. Orbiting spacecraft spotted gullies that might form from briny groundwater seeping to the surface, while methane spikes detected by Curiosity could hint at buried microbial activity or just geological tricks. Either way, Mars has rewritten the rules for habitability. If life took hold on two neighboring planets in the same solar system, how common might it be across the galaxy? That question drives missions like Europe's ExoMars rover, set to drill deep for biosignatures, and NASA's ambitious plan to one day send humans to search in person. Yet for all its promise, Mars isn't the only place in our cosmic backyard hiding liquid surprises. Just as we began piecing together its damp history, another revelation was brewing 500 million miles away, where icy moons around Jupiter were caught hiding oceans far greater than Earth's beneath shells of frozen crust. Europa and Enceladus were supposed to be frozen wastelands, lifeless ice marbles drifting in the outer solar system. Instead, they turned out to be two of the most tantalizing real estate for alien life we've ever found. When Galileo's spacecraft swooped past Jupiter's moon Europa in the late 1990s, it didn't just see a cracked, icy shell. It glimpsed a world with a subsurface ocean so vast, it holds more than twice the liquid water of all Earth's oceans combined. Those chaotic fractures crisscrossing its surface, telltale signs of a restless ocean below, flexing and heaving against its frozen ceiling from the gravitational kneading of Jupiter's tides. Then came Cassini's jaw-dropping discovery at Saturn's tiny moon Enceladus. No one expected this 300-mile-wide snowball to be anything but inert, until the spacecraft caught geysers blasting salty water into space from its south pole like cosmic fire hydrants. Sampling those plumes revealed organic molecules, silica nanoparticles hinting at hydrothermal vents, and even molecular hydrogen, a potential energy source for microbes. Suddenly, we weren't just looking at icy moons, we were staring at worlds with all the ingredients for life: liquid water, chemistry, and internal heat from relentless tidal flexing. What makes these ocean worlds revolutionary isn't just their potential to host life, it's how they've rewritten the rules of habitability. Forget the Goldilocks zone. Europa and Enceladus proved liquid water can exist virtually anywhere if you have the right combination of heat and chemistry. Their oceans, sealed under miles of ice, might be shielded from radiation, creating stable environments where life could persist for billions of years. Imagine ecosystems clustered around hydrothermal vents in eternal darkness, much like Earth's deep-sea extremophiles, except here, the entire ocean is the abyss. The implications stretch far beyond our solar system. If icy moons around gas giants can harbor oceans, how many more might orbit the thousands of exoplanets we've discovered? Future missions like Europa Clipper and proposals to dive through Enceladus's plumes aim to hunt for biosignatures, potentially answering whether life is a cosmic fluke or a near-inevitable spark when conditions align. And just as we began grasping the diversity of these hidden oceans, another distant world was waiting to shatter our planetary preconceptions, one that would force us to rethink what makes a planet in the first place. Pluto wasn't supposed to be this interesting frozen relic, a silent bystander at the solar system's edge. But when New Horizons raced past it in July 2015 after a 9-year journey, the images it beamed back shattered every expectation. Instead of a dead, cratered snowball, Pluto greeted us with towering ice mountains of water-hardened bedrock, vast plains of nitrogen glaciers flowing like slow-moving caramel, and a sky hazy with layers of photochemical smog. Even more startling, signs of geological activity, chasms, ridges, and a heart-shaped glacier the size of Texas named Sputnik Planitia, which might still harbor a subsurface ocean sloshing beneath its icy shell. This wasn't just a distant rock, it was a world with its own weather, seasons, and possibly even volcanoes spewing icy sludge. The revelations forced a reckoning. If something as small as Pluto, just 1/6 the mass of our moon, could be so dynamic, what did planet even mean? The debate had simmered since 2006 when astronomers, grappling with a flood of Pluto-like discoveries in the Kuiper belt, demoted it to dwarf planet status. New Horizons didn't just reopen that controversy, it made it irrelevant. Labels aside, Pluto proved that complexity isn't reserved for the inner solar system, it's a universal rule. Yet the mission wasn't finished. 3.5 years later, New Horizons raced past Arakoth, a bi-lobed Kuiper belt object resembling a flattened snowman. This primordial relic, unchanged since the solar system's birth, offered something rare, a time capsule. Its two gently fused lobes suggested planetesimals formed not through violent collisions but slow, gentle mergers, like dust bunnies sticking together in a cosmic breeze. Suddenly, we had a front-row seat to the solar system's assembly process, a clue to how tiny grains became worlds. What made New Horizons revolutionary wasn't just its discoveries, but its message. The outer solar system isn't a static museum. It's a frontier where chemistry, geology, and maybe even biology play out in ways we're only beginning to grasp. And as we turned our gaze back toward the center of it all, another landmark awaited, one that would reveal how the sun, the conductor of our cosmic orchestra, choreographs everything from planetary orbits to the very light that lets us see. The sun has always been more than just a steady beacon in our sky. It's a churning, volatile dynamo with moods that shape the very space around us. For centuries, astronomers sketched sunspots, those dark blemishes dotting its surface, unaware they were glimpsing the edges of colossal magnetic storms. But it wasn't until the space age that we truly grasped the sun's ferocity. Space-based observatories like SOHO, perched in the gravity sweet spot between Earth and the sun, peeled back the layers of our star's atmosphere to reveal a reality far wilder than anyone imagined. Beneath that radiant surface, tangled magnetic fields snap and reconnect like cosmic rubber bands, unleashing solar flares with the energy of 1 billion atomic bombs and hurling coronal mass ejections, clouds of charged plasma across the solar system at millions of miles per hour. One such storm in 1859, the Carrington event, lit up telegraph lines and set papers ablaze in offices, a haunting preview of what could happen to our far more fragile electronic infrastructure today. But the sun's influence doesn't stop at disrupting satellites or painting the northern lights. In the 1950s, Eugene Parker theorized something astonishing. Our star doesn't just shine, it exhales. The solar wind, a ceaseless stream of particles, billows outward in all directions, sculpting a protective bubble around our solar system called the heliosphere. This invisible shield deflects most of the deadly cosmic rays hurtling through the galaxy, making life on Earth possible. Yet when particularly violent gusts of solar wind collide with our planet's magnetic field, they can squeeze it like a stress ball, inducing currents strong enough to fry power grids. What's revolutionary about these discoveries isn't just their impact on Earth, it's how they transformed our understanding of stars everywhere. The same processes that spark solar flares on our sun govern the eruptions of distant red dwarfs and the deadly tantrums of hyperactive young stars. By decoding our stars' rhythms, we've gained a universal key to stellar behavior, from the faintest dwarfs to the most luminous giants. Even the sun's quietest moments teach us. Its 11-year activity cycle, tracked through sunspot counts, mirrors magnetic dances happening in stars we'll never see up close. Yet for all its familiarity, the sun keeps secrets. Why is its outer atmosphere, the corona, millions of degrees hotter than its surface? How do magnetic fields conspire to create the eerily perfect symmetry of coronal loops? Missions like Parker Solar Probe, diving closer to the sun than any spacecraft before, risk melting to find answers. Because here's the paradox: the same star that nurtures us could one day unleash a storm capable of knocking civilization back a century. And as we learn to read the sun's tantrums, another cosmic revelation was waiting, one that would trace the entire life story of stars, from birth to spectacular death. Stars don't just blaze in the sky, they live dramatic, explosive lives, each one a cosmic phoenix burning through its own destiny. At the dawn of the 20th century, astronomers Ejnar Hertzsprung and Henry Norris Russell made a simple graph that would forever change how we see stars. Plotting temperature against brightness, their diagram revealed something unexpected. Stars didn't scatter randomly but clustered into distinct families, red giants hulking in one corner, white dwarfs huddled in another, and the graceful arc of main sequence stars tracing out their prime adulthood. This wasn't just a classification scheme, it was a family album chronicling stellar evolution from birth to twilight. The key to deciphering this cosmic life cycle lay hidden in the heart of stars themselves. In the 1920s, Arthur Eddington theorized that stars powered themselves by fusing hydrogen into helium, a process so efficient, a thimbleful of hydrogen could outshine a city if fully ignited. Later, Hans Bethe mapped the precise nuclear dances that keep stars shining, from the proton-proton chains in modest stars like our Sun to the carbon-nitrogen-oxygen cycle driving massive blue giants. Suddenly, starlight wasn't just illumination. It was the heartbeat of elemental alchemy, forging atoms in furnaces hotter than anything on Earth. But the most stunning revelation came when astronomers traced what happens when stars die. A modest star like our Sun will gently shed its outer layers, leaving behind a glowing ember called a white dwarf. Massive stars, though, they go out with a bang, literally. A supernova explosion can outshine an entire galaxy for weeks, its shockwaves seeding space with the building blocks of planets and life. Iron for your blood, calcium for your bones, even the gold in your jewelry. Every heavy element in the periodic table, from the oxygen we breathe to the silicon in our sand, was forged in these violent final moments. This understanding didn't just rewrite astronomy, it reshaped our origin story. The carbon in your DNA, the iron in your blood, they didn't form on Earth. They were born in the cores of ancient stars that died before our solar system existed. Their remains scattered across space by supernova and stellar winds, only to coalesce into planets and eventually into us. We aren't merely observers of the cosmos, we're its living archives carrying stardust in every cell. Yet some stellar corpses refuse to fade quietly. When Jocelyn Bell detected a rhythmic pulse of radio waves in 1967, she stumbled upon one of nature's most precise clocks, a pulsar, the spinning core of a dead star, flashing like a cosmic lighthouse with metronomic precision. These neutron stars pack more mass than the Sun into a sphere the size of Manhattan. Their gravity so intense a sugar cube-sized chunk would weigh as much as a mountain. And as we'll see next, their eerie signals would open yet another window into the universe's hidden workings. Jocelyn Bell Burnell's meticulous scans of the night sky in 1967 weren't hunting aliens, but for a moment she thought she'd found them. Those rhythmic blips of radio noise arriving every 1.337 seconds with uncanny precision seemed too artificial to be natural. Dubbed LGM-1 for Little Green Men, the signal sparked cautious excitement. Had humanity just intercepted a cosmic beacon? The truth was even stranger. What Bell had stumbled upon was a pulsar, a city-sized corpse of a star, spinning faster than a kitchen blender and blasting beams of radiation like a celestial lighthouse with every rotation. These cosmic metronomes are neutron stars, the densest objects this side of a black hole, packing a sun's worth of mass into a sphere no wider than Manhattan. Born in the supernova death throes of massive stars, their crushing gravity squeezes atoms into a sea of neutrons, creating a teaspoon of material that would weigh 1 billion tons on Earth. But it's their spin that makes them extraordinary. As they rotate, their intense magnetic fields funnel radiation into narrow jets that sweep across space like the beam of a searchlight. When one points at Earth, we catch a pulse. Pulsars don't just dazzle with their precision. They've become universal laboratories for testing physics under conditions no lab could ever replicate. When a pulsar's signal passes near a massive object, its rhythm slows ever so slightly, an effect predicted by Einstein's general relativity, confirming that gravity bends not just light but time itself. Then came the jackpot, the discovery of a binary pulsar in 1974, two neutron stars waltzing around each other while beaming ticks into the void. Over decades, their orbits decayed exactly as Einstein's equations predicted, energy leaking away as gravitational waves, long before LIGO would detect them directly. Beyond relativity, pulsars illuminate the galaxy's hidden corners. Their signals flicker as they traverse clouds of interstellar gas, revealing the Milky Way's invisible structure. Some, called millisecond pulsars, spin hundreds of times per second, whipped up by stolen gas from a companion star, nature's stopwatch, accurate enough to rival atomic clocks. There's even a growing catalogue of pulsars whose combined timing could one day form a galactic GPS, guiding spacecraft between the stars. Yet for all their predictability, pulsars still surprise us. Magnetars, a rare breed with magnetic fields 1,000 trillion times stronger than Earth's, occasionally unleash starquakes so violent they briefly outshine the entire galaxy. Others, like the famous Crab pulsar, sit at the heart of supernova remnants, their relentless energy lighting up the debris of their own explosive birth. Each discovery peels back another layer of neutron star enigmas. What exotic states of matter lurk in their cores? Could some pulsars actually be quark stars even denser than neutron matter? As we unravel these spinning riddles, another class of cosmic beacons was waiting to rewrite the story of the early universe. One so bright they outshone galaxies, yet so distant their light had traveled billions of years to reach us. Quasars weren't just brilliant oddities, they were windows into a time when the cosmos was young, violent, and teeming with supermassive black holes feeding frenzies. Quasars didn't just confuse astronomers, they rewrote the rules of what we thought was possible. When Martin Schmidt first deciphered the spectrum of Quasar 3C273 in 1963, the numbers made no sense. Its light was shifted so far into the red, it implied the object was fleeing at nearly a third the speed of light, billions of light years away. Yet it shone brighter than 100 Milky Ways crammed together. How could something so distant outshine every star in its galaxy? The answer lay in a cosmic monster, a supermassive black hole, billions of times heavier than our sun, gorging on gas and stars with such ferocity that its accretion disk glowed white-hot, beaming energy across the cosmos like a lighthouse through fog. These weren't just overachieving stars. Quasars were the adolescent growing pains of galaxies. As telescopes peered deeper, they revealed a universe teeming with these brilliant beacons, all flickering in the early cosmic dawn. The most distant quasar found to date, J0313-1806, blazed when the universe was just 670 million years old, a toddler by cosmic standards. Its existence proved black holes weren't slow growers. They ballooned to gargantuan sizes almost instantly after the Big Bang, a mystery that still keeps theorists awake at night. But quasars offer more than just a window into galactic puberty. Their light, filtering through billion-year-old clouds of gas, carries chemical fingerprints of the early universe's composition. Like cosmic backlighting, they've mapped the web of intergalactic hydrogen, revealing the scaffolding upon which galaxies assembled. Some even sport jets stretching millions of light years, particle cannons so powerful they could sterilize entire solar systems in their path. What makes this discovery revolutionary isn't just the scale of quasars' violence, it's how they've humbled our cosmic timeline. These objects proved that black holes didn't form leisurely over eons. They were there from nearly the beginning, shaping galaxies from the inside out. Today, most quasars have gone quiet, their black holes sated after devouring the last scraps of nearby matter. But their legacy lingers in every modern galaxy's core, including our own Milky Way, where Sagittarius, a star, slumbers, a relic of a more gluttonous youth. Just as quasars revealed the universe's fiery adolescence, another phenomenon was waiting in the shadows, one so brief and brilliant, it would make quasars look like candle flames. Gamma-ray bursts, the cosmos's most powerful explosions, would next force us to confront the violent deaths of stars on a scale we'd never imagined. Gamma-ray bursts weren't just mysterious, they were cosmic false alarms that turned out to be the most violent event since the Big Bang. When Cold War satellites in the 1960s detected sudden spikes of gamma rays, military analysts initially suspected nuclear tests until they realized the blasts were coming from deep space, not Earth. For decades, these fleeting flashes of high-energy light, lasting anywhere from milliseconds to minutes, defied explanation. Were they local oddities or universe-shaking cataclysms? The answer, when it finally came, was staggering. These bursts were the death screams of massive stars collapsing into black holes, or neutron stars merging in titanic collisions, events so powerful they could outshine 1,000,000 trillion suns for a heartbeat in time. Take the infamous BOAT, the brightest of all time, a gamma-ray burst detected in October 2022. Though it lasted barely 10 hours, it unleashed more energy than our sun will emit across its entire 10 billion-year lifespan. That's like compressing every lightning strike, every volcanic eruption, and every supernova in history into a single cosmic firecracker. But what makes these explosions revolutionary isn't just their raw power, it's how they've illuminated the universe's darkest corners. Long bursts lasting over 2 seconds signal the collapse of massive stars into black holes, while short bursts, often less than a second, betray the violent mergers of neutron stars. And in August 2017, we hit the jackpot. A short burst detected simultaneously in gamma rays and gravitational waves, marking the birth of multi-messenger astronomy. That neutron star collision wasn't just a light show. It was a cosmic alchemy lab. As the two ultra-dense corpses spiraled together, they sprayed space with newly forged heavy elements: gold, platinum, uranium, even the iodine in your thyroid. Suddenly, gamma-ray bursts weren't just destroyers, they were creators, seeding the universe with the building blocks of planets and life. Their brilliant afterglows also serve as backlights, revealing distant gas clouds and the structure of the early cosmos. Some bursts hail from galaxies so far away, their light has traveled over 13 billion years to reach us, snapshots of the universe in its infancy. Yet mysteries linger. Why do some collapsing stars produce gamma-ray bursts while others fizzle into quiet black holes? Could a nearby burst strip Earth's ozone layer, triggering mass extinction? Even now, satellites like Swift and Fermi scan the skies for these cosmic flashbulbs, while future observatories aim to catch the very first bursts from the dawn of time. And as we piece together their role in shaping the universe, another revelation was quietly taking shape, one that would map the hidden scaffolding upon which all galaxies are strung like dew on a spiderweb. Galaxies aren't driftwood scattered randomly across the cosmic ocean, they're beads strung along invisible threads, part of a tapestry so vast it defies human scale. When astronomers first mapped millions of galaxies through projects like the Sloan Digital Sky Survey, they expected chaos. Instead, they uncovered an eerie order, galaxies clustering along sprawling filaments, intersecting at dense nodes, with yawning voids between them stretching hundreds of millions of light years. This cosmic web spanning the observable universe isn't just a pattern, it's a fossil record of how gravity sculpted everything we see. The real revelation came when simulations replayed the universe's history. Starting with the nearly uniform soup of the early cosmos, tiny quantum ripples seen as faint temperature variations in the cosmic microwave background got amplified over billions of years. Dark matter, that invisible scaffolding, clumped first, its gravity dragging ordinary matter into filamentary rivers. Galaxies formed where these streams crossed like cities at the junctions of ancient trade routes. What's staggering is how perfectly simulations like the Millennium Run mirrored reality, tracing web-like structures that matched galaxy surveys down to the finest details. This blueprint of cosmic architecture answers questions we didn't even know to ask. Why do galaxy clusters often appear lined up like pearls on a string? Why do some regions of space seem eerily empty? The web explains it all. Even our own Milky Way resides in a modest filament, part of the Laniakea supercluster, a sprawling metropolis of 100,000 galaxies, all flowing toward a gravitational nexus called the Great Attractor. Yet the cosmic web's greatest gift might be what it reveals about dark matter. The way filaments bend light, gravitational lensing, lets us weigh the unseen scaffolding directly, proving dark matter isn't just a placeholder in equations. It's the universe's master architect quietly dictating where stars and galaxies would shine. And as we marvel at this intricate structure, a pressing question lingers. How did the early universe start so smooth, so perfectly primed for this web to form? The answer lies in a theory so radical it rewrote cosmic history in a fraction of a second. The early universe had a problem: it was too perfectly balanced. Every direction we look, the cosmic microwave background shows near identical temperatures, yet regions billions of light years apart couldn't have possibly exchanged heat in the universe's infancy. It's like walking into a library where every book, despite never leaving their shelves, mysteriously fell open to the exact same page. In the late 1970s, physicist Alan Guth wrestled with this conundrum until he struck upon a radical solution: cosmic inflation, a runaway expansion so violent it stretched space itself faster than light could chase it. Picture the universe's first trillionth of a trillionth of a trillionth of a second, a speck of pure energy smaller than a proton. Then, in less time than it takes light to cross that tiny distance, inflation ballooned it to the size of a grapefruit, smoothing wrinkles like a cosmic steam iron. This exponential growth spurt didn't just explain the universe's eerie uniformity, it answered why space appears geometrically flat, why we don't find bizarre magnetic relics called monopoles, and how quantum fluctuations got stretched into the seeds of galaxies. The kicker: we might be seeing inflation's fingerprints in the faint swirls of the cosmic microwave background, where primordial gravitational waves could have left their mark. But inflation's wildest implication isn't about our universe, it's about what lies beyond. If space could inflate once, why not endlessly, birthing countless bubble universes with different physical laws? Some might have stronger gravity, others no atoms at all. our cosmic home in this view becomes just one page in an infinite multiverse library. While definitive proof remains elusive, inflation's explanatory power has made it cosmology's leading origin story, transforming the Big Bang from a singular event into something far richer, a cosmic chain reaction where universes sprout from quantum foam like dandelions in a field. As mind-bending as inflation seems, the universe left another measuring tape in its wake. Etched into the distribution of galaxies are faint echoes of sound waves from the primordial plasma, a ruler so precise it lets us measure cosmic expansion across billions of years. These Baryon acoustic oscillations don't just map where galaxies live, they reveal how the universe grew up. Imagine the universe's infancy as a cosmic orchestra, its dense plasma vibrating with sound waves that would leave echoes for eternity. When the first atoms formed around 380,000 years after the Big Bang, those primordial pressure waves froze in place like a phonograph record pressed into the fabric of spacetime itself. Today, we can still read those grooves, not with our ears, but through the precise clustering of galaxies. These fossilized vibrations, called Baryon acoustic oscillations, stretch roughly 500 million light-years from peak to peak, a standard ruler etched into the cosmos. What makes BAO revolutionary isn't just their existence, it's how they've become one of our most trustworthy yardsticks for measuring the universe's expansion. Unlike supernova or Cepheids, which rely on tricky brightness calibrations, BAO offer a geometric measure. By surveying millions of galaxies, astronomers can spot that characteristic 500 million light-year separation like a baker checking the consistency of a ruler in every loaf. When the Sloan Digital Sky Survey first mapped this pattern in the 2000s, it didn't just confirm the universe's accelerated expansion, it provided independent proof of dark energy's grip, matching findings from supernova while sidestepping their potential biases. But BAO's real magic lies in their versatility. These cosmic ripples serve as time capsules, letting us compare how the universe stretched at different epochs. Younger galaxy surveys show BAO compressed, just as theory predicts for an expanding cosmos, while more distant, ancient galaxies reveal the oscillations in their primordial state. Together, they form a cosmic slide rule, tracking how dark energy's repulsive force has wrestled with gravity over billions of years. Yet these subtle fingerprints also test our boldest cosmological theories. Do BAO measurements align perfectly with the cosmic microwave background snapshot of the early universe? Does their scale hint at exotic physics beyond our standard model? Every new galaxy catalog, from DAISY to future projects like Euclid, sharpens this ruler's edge, probing whether dark energy's strength has changed over time or if our understanding of gravity itself needs revision. As BAO continue to refine our cosmic ledger, they've set the stage for an even thornier puzzle. Why two of our most trusted methods for measuring the universe's expansion, rate the Hubble constant, disagree so dramatically it sparked a crisis in cosmology? The universe has been expanding for billions of years, so why can't astronomers agree on how fast it's happening? This isn't just academic quibbling. It's a full-blown cosmic mystery dubbed the Hubble tension, where two of our most trusted methods for measuring the universe's growth rate stubbornly refuse to match. On one side, we have meticulous local measurements, Cepheid variable stars, supernova, even gravitational lensing, all pointing to an expansion rate around 73 kilometers per second per megaparsec. But when we peer back to the universe's infancy using the cosmic microwave background, the math suggests a slower pace, closer to 67. That gap might seem small, but in cosmology, it's like two clocks ticking to entirely different rhythms. What makes this discrepancy so electrifying isn't the numbers themselves, it's what they might be hiding. The early universe's light, preserved in the CMB, tells one story. The nearby cosmos with its glittering galaxies tells another. Either we've overlooked something fundamental in our measurements, or the universe itself changed gears along the way. Some theorists whisper about dark energy growing stronger over time, warping expansion like a car gradually pressing harder on the accelerator. Others propose exotic additions to the particle zoo sterile neutrinos, perhaps altering the cosmic recipe just enough to tweak the numbers. Even gravity itself might play by different rules on the largest scales, a possibility that would send physicists scrambling to rewrite Einstein's playbook. The stakes couldn't be higher. If the Hubble tension holds, it won't just adjust a few decimal places in textbooks. It could crack open the door to physics beyond our standard models, revealing forces or particles we've never dreamed of. Projects like the James Webb Space Telescope are now hunting for flaws in our local measurements, while next-generation CMB experiments scour the ancient sky for hidden clues. This isn't just a puzzle to solve, it's a rare glimpse of the cosmos refusing to fit neatly into our equations, nudging us toward something grander. And as we wrestle with the universe's inconsistent speedometer, another revelation awaits, one that proves even time itself bends to the whims of gravity's relentless grip. Time isn't the steady, universal tick-tock we imagine. It's a shape-shifter, bending under gravity's weight and stretching at high speeds like taffy. Einstein's relativity didn't just tweak our ideas about space, it shattered the illusion of time as a constant, revealing it as deeply personal. Take the satellites orbiting overhead, the very ones guiding your GPS directions. Up there, 20,000 kilometers above Earth, time literally moves faster, by about 38 microseconds each day because gravity's grip is weaker. If engineers didn't adjust for this, your navigation would drift nearly 10 kilometers off course daily. This isn't a theoretical quirk, it's a daily validation of general relativity, baked into the tech we rely on without a second thought. But the extremes are where time dilation gets truly surreal. Near a black hole where gravity warps spacetime like a bowling ball on a trampoline, clocks would crawl from an outsider's perspective. The movie Interstellar wasn't exaggerating. For every hour on the planet Miller, orbiting Gargantua 7 years pass elsewhere. This isn't Hollywood fantasy, it's the universe's brutal math. Even subtler effects play out closer to home. In 1971, scientists flew atomic clocks aboard commercial jets, comparing them to counterparts on the ground. After circling Earth, the airborne clocks were nanoseconds younger, a tiny but irrefutable gap proving time bends for speedsters too. What's revolutionary here isn't just the physics, it's how time dilation forces us to confront time as malleable, not absolute. Your heartbeat, your aging, even your thoughts would unfold differently near a neutron star or at near light speed. Philosophers once debated whether time was a river or an arrow. Einstein showed it's more like a network of streams, each flowing at its own pace. Yet for all its strangeness, this fluidity isn't chaos. It's precisely predictable, woven into the cosmos's fabric. And just as relativity redefined time, another theory would challenge reality's very foundations, one where particles flicker in and out of existence, and the vacuum of space teems with quantum potential. The boundary between cosmology and quantum mechanics wasn't just blurring, it was about to collapse entirely. The universe's grandest structures, its galaxies, clusters, and sprawling cosmic web, owe their existence to the tiniest of tremors, quantum fluctuations no larger than a billionth of a billionth of a billionth of a meter. In the first incomprehensibly fleeting moments after the Big Bang, these microscopic hiccups in spacetime itself were stretched to cosmic proportions by inflation, that runaway expansion that turned subatomic wrinkles into gravitational wells vast enough to cradle entire superclusters. What's staggering isn't just the scale of this transformation, it's the profound irony that the universe's most majestic features were sculpted by quantum randomness, the same capricious forces that make electrons dart unpredictably around atoms. Those faint temperature variations we see in the cosmic microwave background, They're fossilized imprints of these quantum jitters, frozen into the universe's fabric when light first broke free. Over billions of years, gravity amplified these subtle density differences, pulling matter into the web of galaxies we recognize today. Simulations tracing this growth reveal an uncanny match. When physicists seed virtual universes with quantum fluctuations scaled up by inflation, they evolve into structures eerily resembling our actual cosmic surveys, down to the placement of filamentary bridges between galaxy clusters. But the real frontier lies in pushing this connection even further back to the moment when quantum gravity, a theory still in its infancy, might explain the Big Bang itself. Some models suggest the entire universe could have quantum tunneled into existence from literal nothingness, a fluctuation in the same probabilistic arena that governs particles. Others propose that the seeds of cosmic structure were sown before inflation, in a quantum foam where spacetime itself bubbled and churned. While these ideas remain speculative, they point toward a breathtaking possibility that the universe's largest and smallest scales aren't just linked metaphorically, but through a unified physics we've yet to fully grasp. This landmark doesn't just rewrite cosmic history, it redefines our place within it. The galaxies we admire, the voids we map, even the atoms in our bodies ultimately trace their origins to quantum vibrations so small they defy visualization. We're left with a humbling realization. The universe's grand design emerges not from some predetermined blueprint, but from the same fundamental uncertainty that makes reality shimmer at its core. And as we unravel how quantum randomness shaped the past, another question looms: how will the universe's own quantum quirks dictate its final fate? The universe's final act won't be a grand explosion or a fiery collapse. It might just be a slow, silent fade into darkness. Based on everything we've measured, the relentless tug of war between dark energy's push and gravity's pull, cosmologists have sketched three haunting possibilities for how it all ends. The first, and most likely, is heat death. Trillions of years from now, galaxies will vanish over the cosmic horizon, stars will burn out, and even black holes will evaporate, leaving only a thin soup of particles too far apart to ever interact again. It's not an explosion but an exhaustion, like embers cooling in an endless void. Then there's the more dramatic Big Rip, a scenario where dark energy grows stronger over time, eventually overpowering every force that holds matter together. First, galaxies would tear apart, then solar systems, and finally, in the last terrifying moments, atoms themselves would be shredded. The universe wouldn't just end, it would unravel stitch by stitch. But here's the twist. Some theories suggest a cyclical universe, where the cosmos collapses and rebounds in an endless cycle of big bangs. The jury's still out because the fate of everything hinges on dark energy's true nature, a mystery we're racing to solve. Observations of distant supernova act as cosmic speedometers, tracking whether expansion accelerates uniformly or intensifies. Galaxy clusters serve as gravity's accounting books, tallying whether matter can ever slow dark energy's march. Even subtle distortions in the cosmic microwave background hint at whether spacetime itself might one day turn hostile. What's fascinating isn't just the science, it's how these scenarios force us to confront time on scales beyond human comprehension. Heat death unfolds over a googol years, a number so vast it dwarfs all the atoms in the visible universe. Yet even this existential chill carries a strange comfort. If the universe must end, let it be with the quiet dignity of equilibrium, not violent dissolution. While we might never witness these final chapters, their study reveals profound truths about the here and now. The same physics dictating the universe's demise also governs galaxy formation, dark matter's grip, and why we're here to ponder it at all. And as we peer into the abyss of deep time, another tool is helping us test these grand theories, not with telescopes, but with supercomputers stitching together virtual universes from the Big Bang to the last flickering light. Supercomputer cosmology doesn't just simulate the universe, it rebuilds it from scratch inside machines the size of tennis courts. Take the Illustris TNG project, one of the most ambitious virtual universes ever coded. It doesn't just trace the birth of a few galaxies, it spawns billions of them, each represented by particles acting out the laws of physics over 13.8 billion simulated years. The numbers defy comprehension, trillions of calculations per second, tracking everything from the gravitational tug of dark matter to the explosive feedback of supernova. Yet what's mesmerizing isn't the raw computing power. It's how these digital cosmos mirror reality with eerie precision, reproducing the web-like structure of galaxy clusters, the distribution of gas in cosmic voids, even the chemical fingerprints of stars. These simulations aren't just cosmic video games, they're laboratories for testing ideas we could never probe in nature. Want to know how a galaxy's shape changes if dark matter interacts with itself? Tweak the code and watch the virtual experiment unfold. Curious whether early black holes stunted or spurred star formation? Run a simulation with and without them and compare the results. When astronomers spotted real galaxies with oddly balanced proportions of old and young stars, it was supercomputer models that cracked the mystery, revealing how supernova winds and black hole jets act like cosmic thermostats, regulating star birth across eons. But the real revolution lies in how these virtual universes guide our eyes to the sky. Before the James Webb Space Telescope launched, simulations predicted where to find the faintest, earliest galaxies. And when its first deep field images arrived, there they were, nestled right where the digital universe said they'd be. Other models, like Millennium TNG, are now mapping hypothetical gravitational wave signals, creating cheat sheets for observatories like LISA to decode the murmurs of colliding black holes. Yet for all their sophistication, these simulations have humbling limits. Even the most detailed can't track every star in a galaxy, resorting to statistical stand-ins for stellar populations. Some quantum processes, like the birth of the first black holes, remain too complex to model exactly. That's where an unexpected partner enters the cosmic discovery pipeline, not supercomputers, but everyday people with curiosity and a knack for pattern recognition. While machines crunch numbers, human eyes, millions of them, are spotting anomalies no algorithm could foresee. Astronomy once belonged to lone observers peering through telescopes, but the digital age has flung the cosmos wide open. Now, anyone with an internet connection can help rewrite celestial textbooks. Take Galaxy Zoo, born from a simple problem. Astronomers had 1 million galaxies to classify from robotic surveys, but no team could possibly examine them all. The solution: crowdsourcing the human brain's knack for pattern recognition. Volunteers, teachers, artists, even school kids began sorting spiral arms from elliptical blobs, uncovering oddities so bizarre they'd slipped past algorithms. One Dutch schoolteacher, Hanny van Arkel, stumbled on a glowing green smudge unlike anything in the archives. Dubbed Hanny's Voorwerp, this cosmic ghost turned out to be a quasar's light echo, a fossilized beam of energy slicing through intergalactic gas, a discovery made possible because human eyes spotted what code missed. But citizen science doesn't just rely on sharp eyes, it harnesses idle computers too. SETI at home transformed millions of laptops and desktops into a virtual supercomputer, sifting radio static for the faintest whisper of alien signals. While ET remains elusive, the project proved something revolutionary. The collective power of everyday devices could outperform the mightiest university servers. Today, platforms like Zooniverse host dozens of projects, from tracking solar storms to hunting exoplanets in Kepler data. When professionals faced a deluge of data from modern telescopes, like the Rubin Observatory's impending fire hose of 47 terabytes nightly, they realized the solution wasn't hiring more PhDs. It was inviting the world to join the search. What's beautiful about this landmark isn't just the discoveries, it's how it demolishes the ivory tower of science. A retiree in Wisconsin might flag a supernova. A teenager in Mumbai could help map Martian weather. These projects remind us that curiosity isn't confined to labs, it's a universal spark. And as telescopes grow larger and datasets more overwhelming, this partnership between pros and public will only deepen because the universe speaks in mysteries too vast for any one group to decode alone. Now, as we stand on the brink of a new observational era, the next generation of telescopes promises to stretch our vision further than ever, not just across space, but back to the very dawn of time. 30th landmark, next generation telescopes, the future of cosmic discovery. The James Webb Space Telescope peers deeper into infrared than ever, studying the first galaxies and exoplanet atmospheres. Extremely large telescopes on Earth will directly image nearby exoplanets. The Square Kilometer Array radio telescope will map cosmic hydrogen in unprecedented detail. These instruments promise to reveal new cosmic landmarks, potentially discovering life beyond Earth or unlocking dark matter's nature. They ensure astronomy's golden age is just beginning. Next, we'll reflect on how these landmarks collectively transformed our cosmic perspective. Imagine a telescope so powerful, it could read the license plate of a car parked on the moon if there were roads up there. That's the kind of revolutionary clarity next-generation observatories are bringing to astronomy. Take the James Webb Space Telescope, humanity's most ambitious time machine. Perched 1,000,000 miles from Earth, its gold-plated mirrors catch infrared light stretched by 13 billion years of cosmic expansion, letting us witness the universe's toddler years, when the first stars flickered to life in a sea of primordial darkness. Already, Webb has shattered expectations, spotting galaxies too mature to exist so soon after the Big Bang, their starlight defying our models of cosmic evolution. But the revolution isn't confined to space. On remote mountaintops in Chile and Hawaii, extremely large telescopes with mirrors wider than blue whales are taking shape. These behemoths will do more than glimpse exoplanets. They'll dissect their atmospheres for biosignatures like oxygen or methane, hunting for the chemical whispers of life. Picture an alien world's weather patterns mapped in real time, or the first definitive detection of photosynthesis on a distant Earth twin. Meanwhile, the Square Kilometer Array, a sprawling network of radio antennas across 2 continents, will trace the universe's skeleton in hydrogen, the same raw material that birthed the first stars. Its sensitivity is so acute, it could detect an airport radar on a planet orbiting a star tens of light years away. What ties these projects together isn't just their staggering specs, it's their potential to answer questions we haven't even thought to ask. Dark matter's particles might finally betray their presence in the gravitational lensing patterns of ancient galaxies. The first black holes could surrender secrets about how they grew so monstrously fast. And lurking in some exoplanet's atmospheric spectrum, a molecule like phosphine, a gas associated with life on Earth, might force us to confront the most profound discovery in human history. We're not alone. Yet these telescopes are more than tools, they're bridges between eras. Just as Galileo's crude spyglass unveiled Jupiter's moons, these instruments will redefine our place in the cosmos all over again. The golden age of astronomy isn't behind us, it's being built, one mirrored segment and radio dish at a time, by engineers and dreamers who refuse to let the universe keep its secrets. From the moment we realized Earth wasn't the center of creation to the startling revelation that 95% of the cosmos is made of invisible dark matter and energy, these 30 cosmic landmarks didn't just expand our knowledge, they shattered our assumptions over and over. What's remarkable isn't just the scale of these breakthroughs, but how they weave together into a single story of human curiosity. every discovery, from Copernicus's heliocentric revelation to the gravitational waves humming through space-time, didn't stand alone. Each one leaned on the insights that came before, proving science isn't a collection of eureka moments but a slow, relentless climb, one where even our mistakes become stepping stones. Take the Hubble telescope, Galileo's crude instrument, little more than a tube with lenses, exposed Jupiter's moons and cracked open the heavens. Centuries later, that same basic tool evolved into Hubble, capturing galaxies so distant their light predates Earth itself. And now, JWST peers even deeper, its infrared eyes revealing infant galaxies that defy our cosmic timelines. That's the essence of scientific progress. Each generation's cutting-edge tool becomes the next footnote, their breakthroughs folded into textbooks as new mysteries take their place. But here's the real wonder: the universe keeps outsmarting us. Just when we think we've mapped its boundaries, it throws us a curveball. Black holes, once deemed mathematical oddities, turned out to power quasars and merge in gravitational symphonies. The vacuum of space, once thought empty, seethes with quantum particles flickering in and out of existence. Even time itself, that steadfast constant of human experience, bends and warps under gravity's grip. The more we learn, the clearer it becomes. Reality is far stranger than any fiction. And yet, for all we've uncovered, the cosmos guards its secrets fiercely. Dark matter still eludes detection, its presence betrayed only by the gravitational tug it exerts on galaxies. Dark energy, that enigmatic force speeding up the universe's expansion, defies every attempt to pin it down. Are these puzzles waiting to be solved, or permanent gaps in our understanding? The answer might lie in the next generation of thinkers, tinkering with ideas we haven't yet imagined, building telescopes that make JWST look quaint. What ties these landmarks together isn't just their grandeur, it's the humility they instill. Every time we've dared to think we've cracked the universe's code, it's handed us a new riddle. But that's the thrill of the chase, the certainty that somewhere, hidden in the spin of a distant pulsar or the whisper of a neutrino, lies the next revelation poised to upend everything. So while we celebrate these 30 cosmic game changers, remember, they're not the finale. They're the prologue to discoveries still waiting in the dark, ready to ignite our wonder all over again. The universe isn't done surprising us, and that's the most exhilarating thought of all. If this voyage through 30 cosmic game changers left you starstruck, you're not alone. Each discovery proves the universe is stranger and more wondrous than we ever imagined. Want to keep unraveling these mysteries with us? Smash that like button and subscribe to stay plugged into our deep dives across space and time. Got a favorite landmark that reshaped how you see the cosmos? Maybe it was the haunting glow of the cosmic microwave background, or the way gravitational waves made space-time sing. Drop your pick in the comments and let's geek out together. Oh, and tap that notification bell so you'll never miss a launch when we explore new frontiers, from quantum black holes to the search for alien megastructures. The universe has spent billions of years hiding its secrets. Let's uncover them side by side.